Okay, good morning everyone. Today we will have lecture 23. Once again, sorry for my recorded video lecture 22. But I hope that you have already watched, all of you, our students already watched that one. Okay, so today we will have lecture 23 and it is quite in sense full of formulation, but point is understanding everything is not that important. Please feel the procedure and please try to understand the approximations we introduce. So our goal is to understand the procedure to derive our final expression. So if we really to be exact, then we must rely on numerical simulation. So if we have just a computer program, then for example, let's say this is our x-axis and our y-axis. What we have to do is actually solve a certain equation called as Poisson equation over this two-dimensional space. Also solve another equation called electron continuity equation over this two-dimensional space. That is actually what we have to do, accurately calculate our goal, the drain current as a function of gate voltage and drain voltage. So actually we can do it. However, it is done by a computer program, and what we wanted to do is, instead of that, we wanted to derive a certain expression for drain current. That is our goal. Of course, we can do it using computer program, but instead of that, we try to our best to derive an analytic expression for this one. So please understand why we have to spend quite a lot of effort to this seemingly not exact approach. So that is practically very important. So I wanted to start from the last part of our previous lecture slide. So in the previous lecture, lecture 22, we introduced the schematic. So vertical direction was defined as x-axis, and our channel direction was defined as y-axis, and unimportant width direction was called as z direction. And now we have a drain current, and in order to calculate drain current, actually we have to integrate our current density. So think about this once again, two-dimensional space. So let's say that here we have source, and here when y equal to L, now we have drain. So we wanted to solve our equations over this two-dimensional space. Okay, so the boundary starts from y equal 0 and ends at y equal to L, and also the boundary starts from x equal to 0 and goes to infinity. Somewhere there we have the end of our system. Of course, practically our electrons are highly concentrated only, yes, certain distance only from this x equal 0, and you know that this distance is just corresponding to several a few nanometers, right? So this is just nanometer size, and our actual size is corresponding to several micrometer size. So we can just treat this infinity as sufficiently away from this x equal to 0. Then now, whether we consider up to here or up to here, that doesn't matter, because all of our electrons are actually just concentrated on this one. So please think about this one. In this classroom, for example, this blackboard is corresponding to the metal semiconductor interface, x equal to 0 plane, and all over our electron gas is just integrated nearby this blackboard. And if we consider certain integration, vertical integration from starting from here to there, or here to there, here to there. So if I ask you what happens if we extend the boundary of our domain to our calculated electron density, of course there is no change, because even though we extend our integration boundary, but the contribution from this expanded region almost negligible. So simply speaking, anyway, we can consider this a two-dimensional system. Then the quantity we wanted to eventually calculate is ID. This is drain current. What is drain current actually? So if we say drain current, then here we have drain region, and eventually somewhere there we will have certain metal via. So this metal is attached to our highly doped silicon region, so we will have a certain part, so metal silicon interface. This is corresponding to a contact, drain contact. And when we say drain current, actually what we have to do is just this one. Let me just magnify the view over this graph. So let me just draw it here. Here we have this contact, and beyond that now we have, let's say, this is metal, and now we can have n plus region called as drain region. This is drain region. Then when we say drain current, actually what we have to do is just to integrate the current density crossing this green part called as drain contact. This is actually the definition of our ID. So simply speaking, what we have to calculate is this drain current is integration of our current density over certain contact area. So this is contact area, means that drain contact, and we have to calculate this surface integral. Of course, here we have a minus sign, because what we want to calculate is incoming flux from incoming current density from metal into this drain contact or semiconductor device. This is the exact definition, well, good enough definition for drain current. But here we introduce a certain continuity. Yes, say that now we have a certain current. Yes, when we have a certain current, then this current is still conserved, and conserved even at the source current. So what we can say is this ID is, although we write it down as ID, but it is identical to minus IS. In the case of a source, the same amount of current is escaping. So current is coming and escaping, so exactly the same amount. Why we have exact same amount of current flowing into certain device and outcome? Because here we have, in this device, we have only 4 contacts. Please name that. One is called source, and one is called drain, the other is gate, another one is sometimes called as body. However, please note that gate is completely isolated from the silicon area by insulator, so it does not conduct any current. And here we have body. Oh, body is just attached to a silicon, but please note that this body is made of p-type resin. So this p-type resin is isolated from all kinds of our electron transport. For electrons, this p-type body resin is seemingly just a barrier resin, and there is no chance for our electrons move into this p-type resin. So we can say that Ig, the gate current, is identically zero because we have good enough insulator, and also we can say this body current will be quite small because this is just corresponding to the leakage current of a p-n junction, actually two p-n junctions, so this can be quite small. So in this case we can assume the matching between drain current and source current, so we can write down in this way. So let me just come back to our original discussion. So since the current is conservable, then what we can say is like this. If we calculate a certain integration of current density at this point, or integration of current at this point, then what will happen? So there will be certain current conduction over this plane, and also there can be a certain current conduction in this plane. But what we wanted to say is, when we make this integration a certain y value, and if we make it another integration at different point, but the integration should be the same. So are you with me? So I mean that. So please have a look at this line. So here I just make an integration of current density at a certain y position, and regardless the value of y, its value should be the same. Why? If we don't have this constantness, it means that here we have a certain current comes in and only small current is escaping. Then what happens? So anyhow current should be conserved. However, there is no other way for us to generate or demolish our current, so it's not allowed here. So every time we must have the same amount of current. That is explained here. So details are explained in our lecture material. For example, sine or g-directional width. Please have a look at this one. The point is, okay, when we just make an integration, the integration should give us the same value, and point wise we have these different values. Please have a look at this one. Here we have mobility and electron density and gradient of quasi-Fermi potential, electron quasi-Fermi potential. However, this integration is only performed on our x-axis. So why we perform just x-axis? I'm just saying that we should make area surface integration, but why I do just 1D integration? So another direction is just consumed in this W, because we consider g-directional uniformity. So this is really corresponding to the two-dimensional integration. And you know that we have made a really important assumption that our electron quasi-Fermi potential is actually a function of only y. So only electron quasi-Fermi potential changed along channel direction, not changing along x direction. So this dependence is gone. So this is really an important approximation. So, and you know, the justification of this approximation already explained in our lecture 22, because we have only y directional current density. There is no x directional current density. That justifies our approximation of uniformity along x direction. Okay, so then let me just move on. So I think that was already covered in our previous lecture. So let me just start today's lecture. If I remember correctly, so we were there at the end of our previous lecture. So since the current is constant everywhere, so when we integrate over our length scale L, then that will give us just L times ID. So this L is just given into the right hand side. That's the reason why now we have this important relation. So please have a look at here. ID is simply proportional to the effective mobility. Of course, then what is effective mobility? Then we have to be a little bit careful about that. But for y, just to consider this effective mobility as a given number, and W over L. W is width of your transistor. It means that if you have just a wider and wider device, then your current will be increasing and increasing. If you have a 10 times wider device, then you will have 10 times more current. That is not that difficult. And here we have another dependency like inverse dependency on length scale. So this is important. It means that if you have shorter channel device, then you can have higher drain current. That is actually corresponding to the key of miniaturization. So for example, let's usually semiconductor engineers always try to compare their product to a car industry. This is quite a typical way, so I also wanted to follow that analogy. Think about a car. So if you make a miniaturization of a car, so if we have a real car into just a toy car, so do you expect a more expensive and more powerful and more comfortable high performance car when you make it quite small? So usually not. So if you wanted to make something in the car industry, luxury and quite comfortable, then you have to have a certain size. However, in this transistor technology, if you make it small, then due to this factor, this L factor in the lower part of this multiplication factor, you always get higher performance. Means that you have a strong desire to shrink your device. If you, for example, when you just make it small, let's say that the current is the same, then we will have less desire to make it small. However, in this special industry called as semiconductor industry, when we make it small, then we can integrate more devices into the same silicon area at the same time. This is the economics. But another one is at the same time we have strong boost or increase of our performance. Both of performance and economics are advantageous to our scaling, miniaturization. So that is a critical point. So why semiconductor companies are always trying to make smaller and smaller devices? It is because when you make it small, not only it becomes cheaper, but it becomes also more powerful. So that is one thing. And please have a look at this final integration. Today we will focus on this integration because this integration can be switched this way, that way. So that is our main concern today. Well, here starting from 0, why we have 0? Because we assume the source contact is grounded, and here actually what we have to do is the quasi-Fermi potential of source side. But you know that quasi-Fermi potential at source side is identical to the source voltage itself. So since the source is grounded, now we have this 0. And here actually what we have to do is the drain side quasi-Fermi potential, but that is actually corresponding to the voltage applied to our drain terminal. So that's the reason why we have VDS and 0. So in this case, so well, good, but the real problem is then how can you calculate this Q as a function of electron quasi-Fermi potential, and how can we make this integration? This is quite a long story, so I wanted to just make an advertisement up to this page 7. We will just try to most rigorous known to us. Okay, so this up to here, without any further approximation, we can do it. That is known already in 1966. But please note that, so once again, Tower equation 3.13 is the result, and in order to calculate this drain current, what we have to do is just to perform this integral twice, d phi integration, dv integration. When we perform this double integral, then we can accurately calculate ID within the boundary of what? Boundary of gradual channel approximation. We already made an approximation. What was it? That was gradual channel approximation. We just assume that our Poisson equation can be considered just one-dimensional, not two-dimensional. But you will find that this is too complicated and it is just overwhelming. And when you actually try to calculate, so you wanted to find even more simpler expression. So if we will spend a long time on this one. So as a result of this, all of this calculation, then finally, I'm sorry about that. So now in this page 15, we will find this expression. So please make a comparison between our previous double integral and this expression. Previously, when I just show you the Pausa double integral, it was involved with a certain integration over potential and also surface potential and also quasi-Fermi potential. There was a twice integration, and please have a look at this Tower equation 3.21. Can you see the integration? So actually not. Then please have a look at this final result. Yes, this one is just assumed as a number, and you know W and you know L. Yes. How about this one? Oxide capacitance. Can you calculate it? Yes. So when you know the oxide thickness, then by simple calculation you can understand oxide thickness. And how about gate voltage? Do you know gate voltage? Yes, because you apply certain voltage, so you know this one. And flat band voltage is also known. This summer voltage is also known because you are working, for example, 300 Kelvin, you know it. Then here we have something not that easy, so that is surface potential. Yes, this is a problem. Okay, then let's go to the another numbers. And other part is here we have Cox again. That's not a problem. And how about this square of surface potential? Once we know surface potential, then we can calculate its square. And here we have other seemingly quite complicated numbers, but permittivity of silicon. This is a material parameter. Q is just a universal constant, and this is a doping concentration, so you know it. And how about this phi? It's power 1.5. Yes, once you know surface potential, also you calculate it. Others are also the same. So this is the summer voltage once again, permittivity Q, Na, everything is just known. And here we have phi s. So please have a look at once again tower equation 3.21. Although seemingly quite complicated, but it just says that all other quantities are already known, and these green colored ones are just power of our surface potential. It means that when we can calculate surface potential, then we can calculate it. But this is not just a simple equation, but here we have this vertical line and upper bound and lower bound. What is this expression? This expression just says that for phi s, first insert this phi s comma d and evaluate it. And next, please calculate phi sub s comma s and once again evaluate it. And please take the difference between these two components. So are you with me? So for example, you know x square 0 to 2. If you have this kind of expression, how do you calculate it? So first insert 2 into your x, you just calculate the square of 2 and take the difference between this number and square of 0. Then you will have just number 4. Just similarly to this expression, using this equation 3.21, first you have to evaluate this long expression with your surface potential at drain side and surface potential at source side, and evaluate this twice and take the difference. Then you will get the drain current. So to some of you, maybe you may think that this way, wow, even though professor, instructor, myself explained quite a lot, but it seems too complicated. But when we consider the difficulty or complexity of our original double integration, it is just nothing. So there is no integration is involved. What we have to do is just to evaluate this seemingly long expression with given numbers, phi s at source side and phi s at drain side. Then next question is, how can you calculate source side potential and drain side surface potential? These two quantities we can calculate by using our MOS equation. So do you remember our MOS equation? So we considered the voltage division between oxide and semiconductor. By solving that one-dimensional solution equation, we were able to calculate surface potential, and we can apply it twice, two boundary values. So overall computational burden is like this. So when you have a certain gate voltage, so we must gate voltage and also drain voltage, we must calculate this surface potentials at source side and drain side surface potential. Once you calculate this one, of course, this is MOS equation is a non-linear equation. Therefore, in order to solve these two quantities, you have to use a certain computer program or other graphical way. then after that, so I have to admit that this takes some effort. Once you get this value and this value, then the remaining task is just on evaluation. So evaluate this quantity once, twice, and take the difference. Then that will give you the answer. Now, so that was a spoiler to everybody. So now, in order to obtain this kind of a simplification, so first of all, let me just start from the most rigorous way, called as Pausa integration. After that, introduce certain approximations to make a achievable simplification. Okay, so are you with me? So I hope that this was a good motivating discussion for this seemingly long procedure. Why we bother by this kind of long derivation? So because in the MOS modeling, calculation of drain current is most important one, because calculation of gate terminal current, that is just at secondary importance, because that is extremely small. Substrate current, yes, that is also secondary important, but calculation of drain current, that is most important one. So we are spending our every effort on this point. Okay, so now we have just a certain 40 minutes, but I will do my best so to explain more achievable to you. Okay, so now we have strong motivation that anyhow we have to calculate this integration. Otherwise, we cannot calculate drain current. But calculation of drain current is too important to us, so we wanted to develop our analytic way. So then, how can we find this quantity? Inversion charge density. Of course, inversion charge density is simply given by just integration of our electron density. So if we consider this vertical axis, and if we draw electron density as another axis, then we assume that rapid exponential decrease of our electron density. So if we make just the integration of this electron density, then that will give us integrated electron density, and each electron has minus q as its charge, so we can just multiply minus q. So this q sub I is nothing but just a converted value of integrated electron density. Okay, so also please note that this integration is not performed in a y direction, but this vertical direction. This is the vertical direction of our MOS system. So in this case, now we can assume that okay, so now we can assume this dx can be just expressed as d phi and d phi. These all of them just give us dx. In order to do that, we must assume this relation. There is a one-to-one relation between potential and position x. Can we assume such kind of one-to-one relation? Please think about this one. Here we have x-axis, and this is corresponding to x equal to 0. And of course, if we go to deep inside into this system, then our result will be just 0. Why? Because our potential right now is reference to the deep substrate value. After that, there will be certain almost parabolic behavior, and at the end of this journey, when we have x equal to 0, then this one is corresponding to the surface potential. So please think about this one. When we change your x value, how about the change of your potential? Is there any one-to-one relation between them? Okay, for example, if you have a certain potential value, then you can identify the corresponding x value. And if you have a certain potential value, then that is corresponding to another x value. If we have, so I wanted to give you another counter example. If we have certain potential profile like this, please think about what happens. So if we have this kind of potential profile, then if we consider certain potential value corresponding to this one, then we can identify multiple x point. Oh, okay, this is the x point corresponding to certain phi, and also here we have another potential point, another point, and another point. So in this case, we cannot make such kind of change of variable. However, fortunately, in this case, we can assume the monotonic behavior of our electrostatic potential with respect to the position. So if we approach it to this surface, then potential is monotonically increasing. So a certain potential value is always corresponding to a certain position. So that's the reason why we were able to make this kind of variable change. Good. Then please have a look at this dx over d phi. This is nothing but inverse of d phi over dx. And what is it? Gradient of potential with respect to x direction. So this is just x directional electric field with minus sign. So here you can see that now we have x directional electric field. Actually we must have a negative sign here. So but why we don't have a negative, change the sign? Instead of changing the sign of the overall vector, we just keep it. And please note that here and there, the upper and lower bound of our integration is just switched. Then you know that is corresponding to the minus sign. So this is corresponding to now this dx over d phi action. And now we have d phi. Then what is it? Now our seemingly quite complicated this integrand, a part of integrand, is just an expression for our electron density. Our electron density is exponentially dependent on what? Exponentially dependent on our electrostatic potential, and inversely exponentially dependent on our electron quasi-Fermi potential. That is the okay. So well, sorry about that. My pencil my pencil is actually the sorry. Please hold on. Okay, so I have now new pencil. Okay, great. So yes, although looks quite complicated, I just insert our usual expression for our electron density. Then please note that, so when we change the integration bound should be this surface potential, but that surface potential can be simply calculated from our MOS equation. So this is our MOS equation. So please note that this is just a typical, and this part is corresponding to the QS, our silicon charge, of course normalized by Cox, and looks so simple. Why we have so simple expression, this red dashed line? Actually we have other terms corresponding to hole density and other terms. However, all of them are just neglected because, you know, when we consider depletion region or inversion region, then all of those terms are so small, so we can safely neglect them. Only two important terms are kept in this equation 3.14. Then maybe you can ask me the question, is it allowed? Yes, if we restrict ourselves to the depletion region and inversion region, then we are quite safe to use only this simplified one. Okay, so by solving this simplified MOS equation, you can always calculate your surface potential. Actually, this is the procedure we need eventually. So, as I told you in my advertise or spoiler part, so eventually we have to calculate phi s at source side and phi s at drain side. Then how can we calculate these two values? The trick is nothing but just to solve this MOS equation. MOS equation at each slab, source side and drain side. So you must solve this equation twice numerically in many cases, and for some guys really hate the numerical solution, so they instead introduce additional approximation to avoid numerical solution of this tower 3.14. Yes, so that is, maybe they can try within certain boundary of validity. So of course that is an important research work, because by introducing such a kind of a simplification or approximation, they can save the computational burden significantly. Why we care about the computational burden so much? Because, you know, eventual purpose of all kind of this calculation or this derivation is eventually we wanted to use this expression for billion transistor chip. So inside our semiconductor chip, we have billion transistors, and in order to evaluate the performance of that chip, then we have to do this calculation billion times. So then if you make a small reduction of calculation burden in this stage, then although that seems quite tedious and cumbersome, but that really make a high reward. You can save your computational time significantly, and it allows you the full chip simulation. So that's the reason why, even though from my point of view, I love this one, then I can solve this one with my computer program. That's it. But to more practical guys, even this solution of this simple nonlinear equation seems to be too computationally heavy. They really wanted to make it even further efficient expression for this solution. Okay, so please, this is just another story, more advanced one. So for why, just to say that in principle we can solve this equation 3.14. that is just taken as granted. Then now, since now we can calculate this phi value, please let's come back to this one. So now now we must calculate this equation 3.12, and now we understand this upper bound. Yes, and please think about this all other ones. Yes, now we want to make an integration, and this is an integration variable, and also we can treat this v just a given constant, because we are now performing the vertical integration, and along this vertical position the y, electron quasi-Fermi potential, can be regarded as a constant, so there is nothing more. Only important one is this electric field, but also electric field, x-directional electric field, can be calculated, although that is quite complicated, but we can do it. So this is another story, so we will use this one later and in the second part of our lecture. And so please go to this well-known Poisson double integral. So up to now we have found that Q sub I, inversion charge density, can be obtained by just one simple integration. So when we just insert it, then now eventually have this equation 3.13. So please have a look at this one. Here we have a double integral. That's the reason why this is called as a double integral. And here d phi, although written as d phi, what is the key point of this d phi integral? This d phi integral is just, it is corresponding to x directional integral. And please, this dv integral, although it is written as dv integral, but actually this is originated from dy integral. You know that we have a one-to-one dependence between x and phi, and also we have one-to-one dependence between y and our v, electron quasi-Fermi potential. So this is nothing but just disguised form of our two-dimensional integration, just by introducing change of variables. So we have made this kind of information. Wow. So practically, how can you calculate this double integral? So of course this cannot be done analytically, so let me just consider a numerical way. So first fix a certain v value, then inside this square bracket v can be considered as a constant. After that, what you can do is just to integrate this phi function numerically. Then how can you calculate this electric field? So you can calculate this value from our QS expression. We have a long expression for our QS that is obtained from this one. And yes, so we can do it. And how can you calculate this upper bound of phi sub s? Yes, phi sub s also can be calculated from the solution of our MOS equation. So now for given dv value, anyhow we can calculate the first integral within square bracket. Then next one is just change your v value a little bit further and recalculate. So you must calculate this integral, first integral, inner integral, several times. After that, just make an overall sum of this individual first integral, then that will give you the overall double integral. Seemingly quite complicated. Please think about the computational burden you have to do. What you have to do is, at every time, at every value of your v, then you must calculate this phi s. After that, perform this one-dimensional numerical calculation and remember this one and make a summation. That is overall computational burden you have to spend to this one. But fortunately, what is the beauty of this expression is, this expression does not introduce any further approximation beyond the gradual channel approximation. Yes, gradual channel approximation itself is already an approximation. So adding more approximation is always harmful for our accurate calculation. So we wanted to avoid as much as possible introducing any further approximation. So this power sign integral did it without any further approximation. So this is just, how can I say, king of drain current expression. But we love it, but it is almost impossible to be practically used. So that's the reason why from now on we will introduce certain seemingly crude approximations to have the real practical expressions. So are you all with me? So I think that maybe in this stage all of you feel that, oh, power integral sucks and oh, I hate it. So okay, good. Now let's introduce a further simplification. So this integral is, as I told you before, cannot be calculated analytically, so people do not like it. So although that is accurate, so we introduce another approximation. It is called the charge sheet model or charge sheet approximation. And please think about all of the origin of our complication. What is the main reason why we have this difficulty expression? The reason was we love this one. We love this expression. Yes, if we can express our QI accurately but in a simple way, then we wanted to use this expression. But in the case of our power sign integral, what we have to do was, what we did is just without any further approximation, we just vertically integrated all over our electron density position wise. That was the solution of this expression. Good. But in this charge sheet approximation, charge sheet model, then we intentionally introduce an equation which is not very accurate. Okay, so please note that this was our previous expression for QI obtained by just vertical integration. However, in the case of our QI used in this charge sheet model is just simply given by QS minus QD. QS, semiconductor charge, has two components. One is inversion charge and one is depletion charge. However, in this upper part, we try to calculate QI itself accurately. But in this equation 3.16 charge sheet approximation, please understand our QS itself, this is exact. But our QD expression, depletion charge expression, is an approximate one. So it means that, of course, our QI is not very accurate. So are you with me? So the sum of A and B equal to 100. That is exact. But what is the value of B? So if we have an approximate value of A as 45, then we can, of course, we can say that B is 55. But if A is not exact, although their sum is exactly 100, but of course our estimation for 55 for B is also approximate one. So this is the situation. I mean that QS expression is quite accurate, but point is our approximation QD, we will just use this depletion approximation. So surface potential itself determines the depletion of our surface depletion layer. Is it really true or not? Of course, rigorously it is not the truth. However, please understand we have a phenomena called as surface potential pinning. I mean that if we have real MOS structure, our potential, even when we apply very high gate voltage, it cannot increase any further than our 2 times phi b value. 2 times phi b is the condition for our surface inversion. After that, although we apply much higher gate voltage, but of course surface potential itself increase a little bit, but that increment is much smaller than the increment of our gate voltage. So using that phenomena, so we try to say that it is not that bad, because for high gate voltage this phi s does not grow any further. So once again, this is not accurate as just our power sign integral, but anyhow it makes us, introduce us quite much simplification. So please have a look at, it's a huge impact. So now our QI is written as this equation 3.16, and instead of V, now it contains phi s and phi s in it, because our diffusion charge is written as just the surface potential. So instead of this one, we just wanted to change this one. Okay, of course this QI can be written in that way, or QI is function of surface potential. So you must feel something strange. So up to now I told you that there is one-to-one correspondence between x and phi, and now this guy says that between our V and phi s there is a one-to-one correspondence. But please note that our V value had one-to-one correspondence with our not x position but y position. So please note that this phi and phi s are different. So this phi is really position dependent quantity, and this phi s is nothing but our phi evaluated at x equal to 0 position. So it doesn't have any longer the dependence on x position, and it has only dependence on y position. That's the reason why our phi s can be regarded as a representation of another position variable y. So now they are interchangeable. So this dv integral is now changed to d phi s integral. Of course, that is not coming without cost. Here we have the cost of this conversion. So from just integration of qi, but now we have this transformation factor corresponding to the relation between electrostatic potential and electron quasi-Fermi potential and surface potential. So we had to consider this one. So please have a look at this one. Actually, this qi itself is quite easy to make its integration. Please try to make an integration of this expression. How can you calculate its integral? over phi s. Of course, these are all constant, so that will give us just phi s dependence. And here we have a linear term, so this linear term will yield just half of square phi s. And here we have actually 0.5 power of this quantity phi s, and it will become just phi s 1.5. Yes, of course we have to have this number, this coefficient. But anyway, this equation 3.16 can be quite easily integrated. It means that qi itself, its integral is not that difficult. So if we try to evaluate this integral, then we found that actually this is integral available. However, what happens to this factor dv over d phi s? We will consider this quantity from now on, and it is found that this quantity is quite close to just 1. Oh, if this is really 1, then we are quite happy. It means that we can just integrate our qi, and our qi is really immediately integral available. So that's it. But unfortunately here we have a quantity quite close to 1, but here we have a remaining part. So calculation of this remaining part will be the lecture contents of our remaining 15 or 10 minutes. Okay. So then how can you calculate this dv over d phi? In order to this one, first of all, we have to calculate this expression. When we have this expression, then by taking the first order derivative, we can calculate this dv over d phi s. Then please try to find out this v as a function of surface potential. Where can you find it? So we just skip some slides, so that is now used in this point. So we wanted to calculate quasi-Fermi potential as a function of surface potential. And once again, now we have the MOS equation. And this MOS equation, please note that this is not rigorously exact. Why we have a certain error? Because most rigorously we have to use the full expression for our QS, but this term contains only two major terms for our depletion region and inversion region. So please remember, our QS expression contains exponential minus phi and exponential positive phi, and other terms, or linear term, all of them, but they are all neglected, and now we have only these two terms. But anyhow, in this depletion region or inversion region, so it is good enough. We can believe this equation and can use it. Of course, we have treated this equation as an equation for phi s. That was our interpretation about this equation. When we have certain given values, then we can calculate phi s. When v is given, then we can calculate phi s. But how about the reverse relation? When we have phi s, can we calculate v? The result is shown here. So there is no other approximation. We just make a simple manipulation. Then now we have our electron quasi-Fermi potential at a given point is given as just proportional to electrostatic potential. And please have a look at this one. all kinds of so much complicated term. So we wanted to stop here because that seems to be quite complicated, but please wait for a while. So the lesson of this equation 3.18 is our electron quasi-Fermi potential V is proportional to, linearly proportional to just phi s, and we have some dirty term. So how can we treat this second term? That will be the remaining task. Then in order to calculate now dv over d phi s, then we must take just the first order derivative. Please do that. So when we calculate dv over d phi s, this one is just number 1, and the remaining thing will give us quite a complicated expression, because you know here we have a phi s and here we have a phi s. At the same time we have a log. So first of all, this guys comes to the lower part and blah blah blah. So all of this seems to be quite complicated, but amazingly enough, when you do it, you can make a quite a simple expression. So I did it for you instead. So please have a look at this one. Please recall that this was our previous expression for V, and when we take the first derivative of V with respect to surface potential, and we have of course 1. This is actually dominant one. This is dominant one, but we have the remaining one, and when we just evaluate it, this is the intermediate result. Wow, looks quite complicated, but please wait for a while. So then after simple rearrangement, then we can make this term. Still, this second term seems to be quite complicated, but when we multiply our minus q item, because in order to calculate our current, then actually we have to calculate this one, dv over d phi s, and it's a phi s integration. So we just evaluate this quantity, and this quantity gives us much simpler expression. The overall integration of our drain current expression just given as Qs itself. Why do we have this minus Qs term? It is originated from our major factor number 1. This number 1 gives us just minus Qs term, and now you can understand this second term is originated from our second term of dv over d phi s. Still, it looks quite complicated, and our question is it really important? So how about completely neglected? Well, if we just neglect it, then our life becomes happy, and of course our result becomes quite inaccurate. So how much we can make an approximation on this term? So I will give you the answer. Let me just make a comparison between the first term and second term, and we hope that please first term should be dominant and second term should be negligible, and the answer is shown here. This orange line is corresponding to the first term, and second term is corresponding to, seemingly in this case, almost constant. It does not vary quite much. And on the other hand, the first term is almost a linear function of surface potential. So please, we must calculate the sum of these two terms. So please think about this case. If we have a certain point, if we make a sum of this and that, if we introduce a certain error in this blue one, slight error in this blue one, then how about the overall error of this sum calculation? That is really negligible. So what we have observed is, well, second term is very difficult to calculate, but actually it has a small value, and in many cases it is not that important, but it plays an important role in this point. In this reason, our first term almost vanishes, and now we have only the second term contributing our sum. So I have to admit this second term once again. I have to admit this factor. Although we have drawn the first term and second term together, all together, this second term seems to be almost a constant. However, in reality, if we draw only second term, the second term only, then it is not actually a constant. It also changes a little bit, quite smoothly. But what we are now trying to do is, so this is the behavior of our second term. However, we wanted to say this way. Okay, in this part, actually its value is not important. It is not important. Only at this point or nearby this point, its value is important. So from now on, we will approximate this second term as a constant, but evaluated at this way. So are you with me? It means that instead of this blue curve which shows a little difference, but we will just introduce a constant value evaluated at this point. Of course, how much error is accumulated? The error, for example, at this surface potential will be this small amount, but in this scale, this is really negligible. So that is the hidden method we can make a tractable expression. So are you all with me? So therefore, in this case, in this constant approximation, then now this second term can be approximated as this one. Wow, it is still looks complicated, but it can be just written as this one. A constant and surface potential dependent, and they can be really approximated. So using this condition, so we were able to derive this equation 3.21. That was a long derivation, but now, as I told you at the beginning of our lecture, spoiler part, so now once we have tower equation 3.21, there is no longer any integration involved. The task is now numerically calculate source side surface potential and drain side surface potential and evaluate this simple expression. Then take the difference that will give us the drain current. So that is today's lecture contents. So I think that today's lecture and previous some lectures on this one is the most significant difference between our course today, senior level course, and our previous course on semiconductor devices, which is just given as simply given by qi times d phi over dx and integration something. So we have a much more rigorous derivation on MOSFET drain current. So please, this is at the heart of our entire semester. So please try to understand this derivation procedure. So that semiconductor engineers are based on this expression, and as you can see, they are not just dull guys, just they are doing their best to derive as much as accurate expression within reasonable assumptions. Okay, so that was the end of today's lecture. So however, equation 3.21 still too complicated for some guys. So for some guys, they really want to make even further simplification. So in the lecture 24, let's study some regional approaches about this one. Please note that this expression can be applied to everywhere. Of course, it cannot be applied to, for example, accumulation, whole dominant transport. We have not considered any whole in this calculation. So whole related one is not our concern, because usually we are considering electron dominant depletion and inversion. So it is enough for our all practically important operational point. Okay, thank you for your attention, and that's it.